Alright, so let's talk about Chapter 3, Marine Provinces. And this chapter we're going to talk about the different features on the ocean floor. But the first thing we need to talk about is bathymetry. Bathymetry is the measurement of the ocean's depth and the charting of the shape or topography of the ocean floor. And so it's a two-part thing where you measure the depth, but you also look at what's down at the bottom of the ocean. A lot of the ocean is flat plains, but they do have a lot of interesting features down there. And early methods used what's known as a sounding line. Essentially, it was just a weight at the bottom of a really long line, and people would go out, throw this line down into the ocean, wait till it hits bottom, record where the line is at the surface, pull it up, and measure that length from the weight to where they stopped at, and that would be your depth. So it wasn't super accurate, but for that time it worked out just fine. In 85 BC, we have Poseidonus, and he used a sounding line to measure the ocean depth in the Mediterranean Ocean. He developed what's known as a fathom. At the time, the fathom was just the length of his arms stretched out. And so nowadays, we've standardized it to 6 feet or 1.8 meters, but at the time, it was just whatever his arm length was. And so if other people were trying to use this measurement, it varied a little bit because everybody's arm length is not the same, and it's probably not 6 feet. I know mine is not 6 feet, and so if I were to do this measurement with that unit, then my measurements would be off because I'm fairly certain my arm span is not 6 feet. And some people may have longer arm spans than 6 feet. So it was a unit that was not very accurate at the time that it was developed, but it was definitely something that was widely used and is still used to this day. So nowadays we use what's known as echo sounders, or you guys would know it much better as sonar. But essentially, a device sends out a sound wave into the ocean, and that device measures how long it takes for that sound wave to go down and back, whether it's down to the bottom of the ocean or whatever it is that it's measuring. And from that, then they can tell what the depth is. And in this particular graphic right here, you can see that they were mapping the continental shelf and the continental slope. And what they see is you can see the nice shelf and the nice slope, but they see this additional layer right above the slope, which they're calling a deep scattering layer. And this right here is biology, so it's probably plankton, maybe not so much fish. This seems to be a little bit deep for fish, but maybe plankton, it may be some other sort of organism that's hanging out at a deep depth, and they're sleeping basically, avoiding their predators, and at nighttime they're going to come back up to the surface and feed. And so what's really interesting is that you're able to see that deep scattering layer because that sound wave bounced off of those organisms and came back to the device and said, oh, I hit something. So it's a way to see some really interesting things in the ocean. Now, back in the day, they used that sounding line, which really you couldn't see that scattering layer using that sounding line. But nowadays, we have more sophisticated equipment. And one particular equipment, which is known as the fish, but essentially known as a side scan sonar, and this particular device is dragged behind the boat at some depth, which is determined. So in this case, this image over here, it's at 50 meters deep, and the swath in which it can register or send out sound waves is 30 kilometers on either side. So the reason why they call this one a side scan sonar is it can take it can send out two beams of sound on either side. That allows you to get a maximum of about 60 kilometers image, basically. And so that image down below is what you see from that side scan sonar. This is typically used in deeper waters to map out the ocean floor. As you can see here, there is a small portion in the middle that is not mapped out. That's purely just because of the design. So in that image there, you can see the black line that runs through the middle of that image. That would be the blind spot, basically. But let's see. Oh, we do have another technique, and this technique is primarily used to see what the structure of the ocean floor looks like under the ocean floor. So a side view of it. This is a lower frequency sound, and it's created by an explosion. And so, as you can see in the figure there, the boat is dragging the receiver off the back side. They release a charge that explodes underwater. Those sound waves go down to the bottom of the ocean and penetrate through a number of layers of the ocean floor, and then bounce back up to the receiver. And so the receiver then picks up all of that information. And if you look on the next slide, this is the top image right there. The top graph is what is sent back to the receiver. So you can see a profile of the ocean crest. You can see they also did some drilling at site 977. So they got some geological information from that site. And from here you can kind of see the different features. You see that little hill there, what's known as a Yusuf Ridge. And in the bottom image, you can see that's they inputted all of that information. They put their interpretation off of what they see from that profile, as well as what sort of geological information they got from site 977. So this is just one way of looking to see what's kind of going on in the crust. Now we have these things. So that side scan sonar is really good and was pivotal in early mapping explorations. But now we have what's known as a multi-beam echo sounder. So it's much like that side scan sonar, but it does multiple sound frequencies in order to get a better view of what's going on under the ocean. And this multi-beam echo sounder gets rid of that blind spot that was in the middle of the side scan sonar. The C-beam was the first multi-beam echo sounder, and it can do up to 60 kilometer wide strips of mapping on the seafloor, which is pretty incredible. And there is no blind spots in this one, unlike the side scan sonar. Additionally, so the multi-beam sonar is off of a boat, but we do have some techniques that we use from space. So we use satellites to help determine bathymetry of the ocean floor. And essentially what happens is that satellite sends down a signal down to the Earth's surface. It measures the difference in it measures the difference in sea surface height. So it has what's known as an average sea surface height. And when it sends its signal down, it looks to see if this sea surface height is currently higher or lower than that average. And so if it's higher, then that means that there's probably some sort of bump or little hill out on the seafloor that's causing that slight change in the ocean surface. Or if it's lower than the average height, then there might be some sort of trench or some sort of dip in the ocean crust at that point. So in this particular sense, this one may be a little bit more accurate. It just depends on the resolution of the satellite and the information that it gets. And these differences in sea surface height that it's measuring, we can't see them with our naked eye. It's primarily an electronic thing that can be seen. And so those differences are what's known as anomalies. So you'll either get a positive anomaly if it's bulging, or you'll get a negative anomaly if it's like dipping down or trenching down. So this is a way to indirectly measure ocean depth and ocean topography. So when we look at the two, you can see the top image there is showing you what the bathymetry is like from a ship-based device. And then the bottom image is showing you a satellite topography image. And so both of them, you can see slightly different things going on, right? The ship one may not be doesn't look as detailed as the satellite one does, right? But the satellite one has a little bit more resolution as well too. But there are still some things that the ship one is good at versus the satellite one. And when we look at the combination of the ship and the satellite imagery, this is the map that we get. So we get a very detailed, very structured map that either one by itself wouldn't be able to give you. So now let's take a cross section of an ocean basin, and for the most part, this will be a typical cross section of your ocean basin. So let's start at point A over in Canada on the North American continent. And as you walk into the ocean, you will first walk into the continental margin. We'll get into what the continental margin and all these different things are in a bit, but you'll walk a certain amount and you'll be on the continental margin. Then when you get deep enough, you'll hit the ocean floor, and then you'll hit a mid-ocean ridge. And on the other side of the mid-ocean ridge, you will repeat the process. You'll have ocean basin and a continental margin before you hit point B. So let's look at each one separately. So continental margin has 5 main components to it. You have your continental shelf, you have your shelf break, your continental slope, your continental rise. You have your 4 parts to it. So those are the main things, and those 4 will make up your continental margin. So that entire, from the beach itself to the edge of the continental rise, before it hits the deep ocean, that is your continental margin. Continental margins are still technically considered part of the continent that is just submerged. So even though it is in the ocean, it's still continent. Whereas if we go into the deep ocean, that's oceanic. So the continental shelf, the continental margin area, is about 7.4% of the Earth's ocean area, so it doesn't take up very much space at all. But this particular space is very important for mineral and oil deposits, as well as for biology. So you can see here, again, you have your continental shelf, your shelf break, your continental slope, and then your continental rise before you hit the abyssal plain. So those four right there make up your continental margin. So continental margins come in two varieties. You've got your passive and your active. Your passive is not close to any plate boundary. So let's use the east coast of the United States as an example. There is no plate boundary, there is no tectonic activity, no volcanic activity within that area. So that would be known as a passive margin versus an active margin, which is near a plate boundary and typically will have a lot of tectonic activity, whether it is earthquake or volcanic in nature. It has both of them. Typically, you'll see either transform or convergent plate boundaries. You won't see divergent plate boundaries in active margins. So in passive margins, you will have a very wide shelf, a continental shelf. There is no plate boundary, and typically there is no volcanism. So no tectonic activity, no earthquakes, no volcanoes. Compared to active margins, which does have volcanoes, has a lot of earthquakes. Typically you'll see mountain building, right? Because you'll have your continental arcs occurring, or you have your island arcs. And you will definitely have some sort of plate boundary interaction. So depending on whether you have an active margin or a passive margin, the continental shelf width will differ. So on the west coast of the United States, which has an active margin, you will see that the shelf width is much thinner than on the east coast. You can see the east coast has a much wider continental shelf, and that's primarily due to the fact that a lot of the material on the west coast side is being subducted and being destroyed, whereas on the east coast side, there's nothing destroying it, so it just accumulates. Sea level also determines the continental shelf width. So if you have a higher sea level, then you can expect to have a much wider continental shelf. Versus if the sea level is low, you shouldn't expect to see that much. And also fast-moving currents can either erode or accumulate continental shelf material. So in this case, there's a slower moving current on the west coast side, so it doesn't allow for a lot of, it doesn't bring a lot of material in, whereas the east coast side has a Gulf Stream, which is really fast. It kind of acts as a barrier in a sense where it doesn't allow that continental shelf material to go into the deep ocean, so it kind of just holds it in place. So and therefore allowing it to accumulate more. So let's look at this Gulf Stream again. You can see the Gulf Stream kind of follows the path of the continental shelf. And in the left-hand image there, you can see temperature-wise, its purpose for bringing warmer temperatures up to the polar regions. And again, it's very fast-moving and it meanders, so it creates these rings, which you can see in between the 2 and the 4 dot. There are these 2 green circles surrounded by red and orange, yellow colors. Those are what's known as cold core rings, and that means that as this current is meandering away from the coastline, it creates circular rings that are moving, and they get snipped off from the current itself, and they keep moving into the deep ocean. So they're basically like little eddies in the ocean, and the water in the middle is cold, and so it allows for nutrients to be pushed towards the equator where it's nutrient poor, And then if you look kind of to the left of the number 4, there's going to be like a round circle of yellowish orange color, and that would be known as a warm core ring, and that's just the opposite of the cold core ring. And it takes warm water northward, where it kind of can warm up the atmosphere a little bit north of the Gulf Stream current. Okay, and so proximity to the plate boundary will determine whether you have an active or passive, whether you have a very wide shelf or if you have a very thin shelf, or if you're going to have a very fast moving current. So typically speaking, in the Atlantic, you'll see you don't have a lot of plate boundary interactions in terms of convergence or transform fold. So you typically tend to see greater sediment accumulation in the Atlantic versus the Pacific, where you have tons of subduction zones. So you tend to see thinner sediment, especially when you get closer to the mid-ocean ridges. Those will have very thin sediment accumulations versus if you're by older crusts, you'll see thicker accumulation, but you'll also typically see a destruction of that sediment in that area. All right, so your continental slope is next after the shelf break, but the shelf break is just the transition point between the shelf, the continental shelf, and the continental slope. And the continental slope then acts as a transition between the continent itself and the deep ocean. And so this is the point where you see deep sloping areas, and typically that slope will be anywhere between 4 to 25 degrees. You can, on average, be about 12 miles wide, and it'll be about 12,000 feet deep. So that's your continental shelf. Okay, so it's a rapid change in depth between your shelf, which tends to be more gradual sloping, and your continental rise, which is also more gradual sloping. But your continental rise is essentially material from the continental shelf that is now making its way down to the abyssal plains. So typically you'll see the continental rise looking more like an avalanche and deposited a lot of material down at the bottom. So it just kind of looks like a haphazard amount of material down there. And you'll see what's known as layering of the material, and we'll get to that in a little bit. So you'll see submarine canyons. So these are very deep V-shaped valleys in the continental slope, and this allows for turbidity currents to bring material down into the abyssal plain really quickly. This material flows very quickly, and it creates at the bottom that fan shape, which is known as a turbidity fan. And so you can have multiple turbidity currents going on, and then you'll have layering of the material down at the bottom on top of that fan there. But essentially you'll have material that goes from the mountains that is eroded down. The streams will then carry it down to the ocean, and that submarine canyon will then continue to carry that material down into the deep ocean. So turbidity currents are very strong underwater avalanches, and they carry any sort of muddy debris or material from the continental shelf down to the abyssal plain. They have to be triggered by an event. They don't just happen spontaneously. So much like avalanches that we see on land, these ones are triggered by earthquakes, oversteepening of the sediment on the shelf, hurricanes, or floodwaters. So any of these can trigger a turbidity current. They are very fast moving and very strong, and so if anything were to get in its way, it probably would not survive. So when we look at that circle image down in the bottom right hand corner there, you can see that layering that I was talking about. So your larger materials are going to settle first, and then smaller materials are going to settle next, and finally your silt and your really tiny particles are going to settle last and fill in all of the gaps in between the larger particles. And so each time a turbidity current goes, it's going to create another layer of material. So you're going to get this layered structure of the sediment in this area. And so that turbidity current will create submarine fans, and that fan deposits that material into the abyssal plains. And in the top right image there, you can see the Indus fan, which is the largest submarine fan in the world. It comes off of the Indus River in between Pakistan and India, and that river contributes so much material into the ocean that that fan basically takes up an entire grid section on Earth. So it's very giant. It's many kilometers wide. You can see a sonar image of it down on the bottom right hand there, of a different fan, but still yet a very big one, and it does transport a lot of material down into the ocean. So let's look at the different regions in the ocean, and as you can see here, we've got our euphotic, dysphotic, and aphotic zones, where you have light and no light, and everything within the continental shelf is known as the neritic region, and then everything past that in the abyssal plains region is known as the oceanic. And pretty much everything within the ocean is known as pelagic, but as you go down deep, you get your epipelagic, which is kind of near, still within the euphotic zone, but still around the same area as the neritic region, which is your continental shelf, or continental margin, I should say. And then you get into your mesopelagic, your bathypelagic, your abyssal pelagic, and finally your hadal. Your hadal is really deep, and typically speaking only found in a few places in the ocean. Alright, so that was your continental margin. Now let's talk about the ocean basin. And here are your main features that you find at the bottom of the ocean. You'll see your abyssal plains and your abyssal hills. You'll see submarine canyons. You'll see seamounts, guyutes, which are also table mounts. You'll see mid-ocean ridges, and you will see trenches. Alright, so now remember, you've got your continental shelf, you've got your slope, you've got your rise. You'll then head into the abyssal plains. In your abyssal plains, you will see abyssal hills, and then you will see a mid-ocean ridge generally, and on your ridge you will see transform folds. Okay, so your abyssal plain is essentially what it sounds like. It's just a very flat, featureless expanse of sediment on the ocean floor. It is very common in the Atlantic, not so common in the Pacific. But in your abyssal plain, you will see abyssal hills, and these are small extinct volcanoes, generally not any higher than 650 feet from the ocean floor, measuring up. So these would have been seamounts that are no longer active volcanoes, so they don't produce any volcanic activity, but they have a very distinctive cone shape feature to them. Next, on the next slide, you'll see a cross section of the crust, and you will see that majority of it is abyssal plains, but what you can see below that is there used to be abyssal hills. Where it says seafloor on the top image, you can see there probably was a little bit more abyssal hills there, some seamount, some activity going on there. You can see that abyssal hill still popping up above the sediment, but on the left hand side where it says 2800, you can see that was probably another abyssal hill at some point in time, but now it's completely covered in sediment. And so over time, that abyssal hill that is popping up above the sediment will eventually be covered and no longer be an abyssal hill. You'll see seamounts. So that abyssal hill may have been a seamount at one point in time. And here in Hawaii, we have a lot of seamounts surrounding our islands. But these are just volcanic mountains on the ocean floor, but they do not extend above the ocean surface. So they're completely submerged. They typically are conical in shape. So think about an ice cream cone turned upside down, and that's what a seamount looks like. They can be elliptical, but they still will have some sort of cone shape. They may be formed by hotspots. Sometimes they may be formed off of a hotspot that created an island, like here in Hawaii. So currently, right now, we have Loihi, which is a seamount off the coast of the Big Island, and eventually that will probably turn into an island at the rate that it's going. But seamounts do create what's known as pillow lavas or pillow basalts, and essentially it's just the lava oozing out of the seamount cools down rapidly as it comes in contact with the ocean water. And so it creates this very nice round rock, which kind of looks like a pillow, I guess, to some scientists. And so they have these features around them typically. So that's how you can kind of tell a difference between a seamount and a table mount. So a table mount typically, unlike a seamount, will be have a flat top. So if you think of like a mesa but underwater, that would be your table mount. And table mounts used to be islands at one point in time, but then they left the hotspot, and as they left the hotspot, they began to sink under the ocean floor because of erosion from wind and rain and from waves. And by the time it got to the point of the ocean surface, the top part had been eroded off by the waves and the wind, so that when it finally submerged, it had basically what's known as a buzz cut, right? It has a very flat surface to it and is no longer active. Then you have mid-ocean ridges, which are essentially mountains under the ocean. They are volcanic in nature, and they do actively spread the ocean plates and create new crust. So one example is the Mid-Atlantic Ridge, and this one traverses the entire Atlantic Ocean and is continuously spreading the Atlantic Ocean apart. So it's pushing the African plate and the North American plate away from each other at a pretty slow rate, but still pushing them away nonetheless. And typically mid-ocean ridges are created by rift valleys, and in particular the Mid-Atlantic Ridge started off as a rift valley that cut Pangaea into two separate continents. And Iceland, in particular, rests right on top of the Mid-Atlantic Ridge. So it is a very interesting case where you have a part of an island that's created from hotspot. So you have this basaltic material that's being created, but it's also spreading it. So eventually Iceland will become a pretty large landmass. Rift valleys, here you can see two images of rift valleys, but that's essentially where land is split apart, um, and it causes a depression in the land. Typically you have lots of earthquakes, lots of transform faults within this area. You have fissures and cracks, so it's a very active area, and it's the beginning stages of creating a mid-ocean ridge. Then you have trenches. Your trenches will be formed when you have subduction zones, where you have convergent plate boundaries. And typically, trenches are associated with either island arcs or continental arcs, depending on what the two plates are that are interacting, whether it's two oceanic plates or whether it's a oceanic and continental plate. These features are very active, and typically when you have an island arc, you tend to have very deep trenches associated with those. So there's that. When you look at this image here, you can see majority of the trenches are located in the Pacific Ocean, and that's basically what makes up the Ring of Fire in the Pacific Ocean. Versus the Atlantic, you can see only two small trenches. You see the Puerto Rico Trench and the South Sandwich Trench down in the Southern Ocean. And so because you only have two trenches in the Atlantic Ocean versus the numerous trenches that you have in the Pacific Ocean, the Pacific Ocean will continue to get smaller and smaller as the Atlantic Ocean continues to expand and get larger. So eventually the Atlantic Ocean will become the largest ocean basin, and the Pacific Ocean will be the smaller of the two. So on the next slide here, this is just a cross section of a trench. So here, for example, you have the Philippine plate that the Marianas Islands sits on, and you have the Pacific plate on the right hand side. You can see the Pacific plate is subducting under the Philippine plate because the Pacific plate is the more dense of the two oceanic plates, and therefore creates the Marianas Trench, which is the deepest trench in the ocean. And so all of that material that is being subducted under the Philippine plate is then melted in the asthenosphere, and that melted material rises back up underneath the Philippine plate, creating volcanic islands. So the Marianas Islands are those volcanic islands that are created. And additionally, you have fracture zones and transform faults on the ocean floor. And these transform faults are found on the mid-ocean ridge, where the spreading centers are. And they are perpendicular to the mid-ocean ridge. And so these areas, the transform fault areas, are seismically active, but you'll have fracture zones that are not seismically active, and they basically just act as a tear or a split in the ocean crust. Here on the next slide, you can see a graphical an image of a transform fault, a fracture zone on a mid-ocean ridge. So you can see this mid-ocean ridge has been split into two pieces, and that transform fault that's in between the two ridges is the seismically active region. On either side of the mid-ocean ridge, you have the two fracture zones, and there's no volcanic activity there or any earthquake activity. All of it's within the transform fault. And these transform faults are believed to accommodate the different spreading rates of the mid-ocean ridge. So if you guys remember from an earlier lecture, there were different spreading rates depending on where you were at along the mid-ocean ridge. And so the mid-ocean ridge doesn't spread at the same rate along the entire thing. So in order to accommodate those different spreading rates, scientists theorize that that's the reason why there are transform faults along the mid-ocean ridge. So on the next slide here, you can see an example of a transform fault splitting the East Pacific Rise. So in the past, the East Pacific Rise would have been one single continuous ridge, but at some point, when the spreading rates differed, that transform fault would have been created. And today, in the last image, the third image there, you can see that it has split very far apart from each other to probably accommodate for those different spreading rates. So if one, say the top part of the third image, is spreading at a faster rate, it's going to split away versus the other part that stayed put. That one is going to continue to spread at its slower rate. So that's just one theory about why these transform faults occur on the mid-ocean ridge. Next, you have hydrothermal vents, and these were discovered by the Alvin expedition back in 1977 when they went to the Galapagos Islands. So the Galapagos Islands are very close to the East Pacific Rise, and so these vents are usually found around mid-ocean ridges where there's a lot of volcanic activity, because these vents pump out very hot water that is generally mixed in with a lot of other molecules such as sulfur. So in this example right here, the image on the right shows a black smoker, and that just means that the water that's coming out is rich in sulfur and iron and a lot of other chemicals as well too. But these particular vents can be very hot. So as the name would suggest, hydrothermal, so water and heat. So these basically pump out very hot water. And as you can see, black smokers tend to be about 660 degrees Fahrenheit. But they will rapidly cool off once they get away from the vent to about 73 degrees Fahrenheit. But even though that's a really high temperature, you do still find biology around these vents that thrive and have found a very specific niche in this area. So hydrothermal vents are formed when you have cracks in the ocean floor, and these cracks will bring in seawater into the crust, and these cracks the water will go to an area where magma is near the crust but not coming up. And so as that water travels through the crust, through these cracks, it gets heated. And when it gets heated, it picks up minerals that are leached from the surrounding rocks. And eventually that water will emerge from a central vent. And when that water emerges, it brings all of that minerals that it picked up along the way out into the water column. So on the next slide here, you can see an image of that. And so this vent right here, you can see is pulling in water along the sides there. That's what the blue arrows are. And then the red arrows is the heat that is rising up from the asthenosphere or the mantle, and it's heating up the water there. And as the water gets heated, it picks up material and then it shoots out through the top part of the vent. And in this particular case, it's showing you a black smoker. So this black smoker has methane, hydrogen sulfide, carbon dioxide, iron, magnesium, along with a bunch of other things. But the temperatures that you can see here, so in this particular case, right off of the vent, it's showing you 350 degrees Celsius. But if you extend upwards towards the cloud where things are precipitating, it drastically drops down to 2 degrees C. And if you get even further away, then it drops down to, precipitation occurs at around about 2 degrees C. So that's where the particles that were in solution now are coming out of solution and becoming solid again. And so you can see those particles fall out, drop to the ocean floor, and accumulate and continue to add to this conical shape for this event right here. So what are the different types of hydrothermal vents that we've discovered so far? As I've mentioned before, we have black smokers, and those are black in color. They generally have metal sulfides in them, so you'll see a lot of iron, nickel, copper, and zinc. And they generally have temperatures of about 662 degrees Fahrenheit, but they will drastically decrease in temperature as you get away from the vent. The next type are white smokers, and these are similar to black smokers, except the water that's coming out of the vent is white in color. And these typically have components like barium sulfide, so you're not going to find a lot of iron, nickel, copper, or zinc. Those metal sulfides that were found in black smokers, you're going to find with softer colors and softer materials in these smokers. And they also aren't typically as warm as black smokers are. White smokers can range anywhere from 68 degrees Fahrenheit to 660 degrees Fahrenheit. But again, it will drastically decrease in temperature as you get away from the vent. And lastly, you have warm water vents. Warm water vents are not hot water like the other two, and these ones don't pull out any minerals or metal sulfides when they come out, so they are clear in color, and their temperatures generally are below 86 degrees Fahrenheit. So on the next slide here, you can see the two different types. You have the white smoker on the top and you have the black smoker on the bottom. I didn't have an image of the warm water vents for you, so unfortunately I don't have that image. But you can see the difference in the water that is coming out of the two different vents. On the next slide here, you can see these tube worms that make a home around these vents, and they have specialized in using the chemicals that come out of these vents to produce energy for themselves. So they don't use photosynthesis. They have incorporated bacteria into their reddish skin there that allows them to use chemosynthesis and use the sulfur that is coming out of these vents. And then on the next slide here, you can see other organisms. On the right there, you see these very large mussels that also use a similar type of bacteria to do chemosynthesis, as well as these very large crabs. And those crabs are detritivores, so they eat whatever material is around the vent at the time. So these vent supports a lot of organisms. So in this sense, you have a lot of organisms packed into a really, really small space. But you don't have a huge diversity of organisms like you see on coral reefs. So you'll see like tube worms, clams, and crabs, and that's about it at a hydrothermal vent. Whereas on a coral reef, you'll see tons of different fishes, you'll see all the different corals, you'll see snails, slugs, urchins, sea cucumbers, a whole variety of different organisms, and you would have high biomass. But at a hydrothermal vent, you don't have the diversity, but you do have a high, basically crowded space, because there's a limited amount of space near the vent, and everybody's clamoring to try to get as close to the vent as possible. These organisms use chemosynthesis to produce their food, and the bacteria that they have incorporated into themselves do that. And a vast majority of these organisms are endemic to the vents. So that means that they're found nowhere else in the ocean. The only place you can find them is around a hydrothermal vent. And so to go along with the first point there, these communities are very small. So you don't find them extending too far away from a vent, because they need that sulfur source from the vent in order to do their chemosynthesis. So on the next slide here, you can just see the difference between photosynthesis and chemosynthesis. The top equation there is for photosynthesis. In this particular equation, you do need sunlight, which you don't have in the deep ocean. So you need water, which is H2O. You need carbon dioxide. You need nutrients, light, and sunlight, and it will give you glucose and oxygen. In chemosynthesis, it's a little bit different. You still need oxygen, but you need hydrogen sulfide instead of light. You also need water and carbon dioxide, and all of that combined makes glucose and sulfuric acid? Actually, no. Sulfuric acid is the first one. The H2SO4, I believe, is hydrogen sulfide. Now I'm confused. One of the two. Anyways, you're producing an acid in the end. So that's just some differences between them. And there have been active hydrothermal vents discovered at Loihi. So that's the newest volcano that will be at some point in time popping up above the surface, but right now it's a seamount, and so we do see active hydrothermal vents over there. Here we see Loihi off of the southern coast of the Big Island there. You can see it's still under the ocean. It hasn't quite risen above the ocean surface. It is still about 3,000 feet below the surface, so it has some ways to go, and it will probably rise up above the ocean in maybe about 10,000 years. So if you want to see that, you're going to have to figure out some way of living forever. Otherwise, stay tuned for that. Alright, so that was chapter 3. We will be talking about chapter 4, which is marine sediments, next.